Welcome to Ask and Learn.
All right, we are given a table with various population values over time, and we have a lot of things to do, so I hope you packed a snack because this is going to take us a while. So in part A, we want to come up with an exponential model based on these 2 points from the table, and then we're going to use that model to come up with predictions for 1900 and 1950. So to find the model, we first have to find the value of k. We're going to use our p equals p naught e to the kt population growth equation, and we're going to use these 2 points. So we'll use for our final population 980, and we'll use for our initial population 790, and for time, what has elapsed between the year 1750 and the year 1800 is 50 years, so we'll use a 50 for t, and we're going to solve this for k. So first we divide both sides by 790, and it's going to reduce to 98/79. And then we're going to take the natural log of both sides, and then we're going to divide by 50. So we get k is the natural log of 98/79 over 50. So we can substitute that into our model along with the initial population of 790. And for our model, we have p of t equals 790 e to the power natural log 98/79 over 50 times t. Okay, so we're going to use that to make our prediction for the year 1900. So if it's 1900, then it has been 150 years since the year 1750. So this model assumes that t equals 0 is the year 1750. Okay, so for our prediction for the year 1900, we're going to use t equals 150, substitute that in to our population model, and we get approximately 1,508. Now that's 1,508 million people. The actual value, reading off the table, was 1650. 1650 million people. Okay, we're going to do the same thing for the year 1950. So if it's 1950, then it has been 200 years since the year 1750. So we put 200 into our population model, and we get approximately 1871 million people. The actual value from the table was 2,560. So notice that both of the values we got from this model were lower than the actual values. All right, that entire process we're going to repeat for 2 different ordered pairs and make a different prediction. So for part B, this time we're using 1850 and its population of 1,260 million, and we're using 1900 and its population of 1,650 million, and we're going to go through the same process again. So we need to find the k value for this one using p of t equals p naught e to the kt. And then we'll have our model, and then we can make our predictions. So we're substituting 1650 in for p of t, and we're substituting 1260 in for p naught. And this time, again, 50 years has elapsed from 1850 to 1900. So we have e to the 50k. We're solving this for k. So we're going to start by dividing both sides by 1260, and that fraction will reduce to 55 over 42. 55 over 42 equals e to the 50k. Then we take the natural log of both sides, and then we divide both sides by 50. So we have our k, natural log of 55 over 42 divided by 50. Now we substitute that into our model, and we have p of t equals 1260, the population in the year 1850, times e raised to the power natural log of 55 over 42 over 50 times t. That's the model we're going to use for part B, where t equals 0 is the year 1850. Okay, so the prediction we're making this time, 2 of them, I believe, or is it just one? Just one. We're making a prediction for the year 1950. So the year 1950 would be 100 years since the year 1850. So we're going to use t equals 100. We substitute 100 into our model, and we get approximately 2161 million. Now the actual value in that year, based on our table, was 2560 million. So another case of this model that we came up with giving us a value that's lower than the actual value. Now we have one more time to go. We're going to do part C, same idea. But this time the points we're using are from 1900 with a population of 1650 and from 1950 with a population of 2560. Okay, let's use those values into our population growth equation and find the value of k. So the final value is 2560, the initial value is 1650, and the time that has elapsed is 50 years. Let's divide both sides by 1650, and the fraction will reduce to 256 over 165. Take the natural log of both sides and divide by 50. And that gives us our k value, natural log of 256 over 165, all divided by 50. So we substitute that into our model. P of t equals initial value 1650 times e raised to the power natural log of 256 over 165 over 50 times t. And in this case, t equals 0 is the year 1900. And the prediction we're interested in making for part C is for the year 2000. So the year 2000 is going to be 100 years since the year 1900. So we're going to use t equals 100. Substitute it into our model, put it in the calculator, and we get approximately 3,972 million for the population. Well, the actual population was significantly higher, 6,080 million, and that's over 6 billion people. So why the discrepancy? Well, if you think about what happened between 1900 and 1950 and 2000, significant advances were made in medical technology in the last 50 years or so, and so lifespan would be incredibly altered. We couldn't use a model from the early 1900s because of medical advances.